हेलो। ओ भाई तू पहले सेट कर ले यार इसको। यहाँ 5 बार मेरे को ये नहीं पता बोलना कहाँ से है, क्या शुरू करूँ। Hello, good afternoon students. So today we'll be discussing couple of questions on dual nature of radiations and matter. So we'll start with question number 1. This question has reads out, there are two electrons which are moving with non-relativistic speeds perpendicular to each other. So we are given two electrons and both are moving perpendicular to each other. And it is given that their corresponding de Broglie wavelengths are lambda 1 and lambda 2. So their de Broglie wavelength in the frame of reference of attached to their center of mass is. So what this question is asking for, that we need to calculate the de Broglie wavelength in the frame of reference which is attached to their center of mass. Okay, so let's start with the question. So we are given, here is one of the electron, let's say this is moving in x direction and its velocity is, let's assume v1 I cap. There is another electron which is moving perpendicular to it, so let's say this is the other electron which is moving perpendicular to it, and let's say the velocity is v2 j cap. Okay, so we can easily write down the momentum of both the electrons. Okay, so momentum is, let's say for the electron 1, momentum can be written as P1 is h over lambda 1, and for second we can write P2 as h over lambda 2. So from here we can easily calculate lambda 1, which is nothing but h by mv1, and lambda 2 is h over mv2. Okay, now we have to find out the de Broglie wavelength in the frame of reference attached to their center of mass. Okay, so let's assume there is another electron which actually represents the center of mass frame. Okay, so we can calculate the velocity of 1 with respect to center of mass, or velocity of 2 with respect to center of mass, any of the electron. So if we want to calculate v1 with respect to velocity of center of mass, this can be written as velocity of 1 in ground frame minus velocity of center of mass in ground frame. So velocity of center of mass we can calculate from here. So velocity of center of mass is nothing but this is m1 v1, and because both are electrons, so their masses are equal, so we can easily put mv1, but that's in I cap, plus mv2 j cap over the total mass, which is 2m. So velocity of center of mass can be written as v1 I cap by 2 plus v2 by 2 j cap. Okay, now let's make use of this information and we can calculate velocity of 1 with respect to center of mass. Okay, that can be written as v1, which is v1 I cap, sorry, this can be written as v1 I cap minus velocity of center of mass v1 by 2 I cap plus v2 by 2 j cap. So V1's center of mass can be written as V1 by 2 I cap minus V2 by 2 J cap. Okay. Now from here V1 with respect to center of mass can be written as V1 square by 4 plus V2 square by 4. Okay. Now let me add another slide to it. We can make use of that, or I'll just make use of I'll just put this up a little bit and this up a little bit. Okay. Now velocity of center of mass in center of mass frame. So we can write down lambda 1 with respect to center of mass is h, the momentum of 1 with respect to center of mass, and that can be written as h over mass of the electron into V1 square by 4 plus V2 square by 4. Okay. Now let me make a space here. This can be moved a little bit here. Now I can easily write down from here that lambda 1 center of mass is equal to, I can put value of V1 from this equation. V1 is h over m lambda 1, and from this equation V2 is h over m lambda 2. So simply putting up these values, we will get lambda 1 COM is equal to h over m under the root. This will give us V1, which is h square over m square lambda 1 square into 4 plus h square over m square lambda 2 square into 4. Okay. So this on solving will give us lambda 1 center of mass is simply m and m. If we'll take out, that will cancel out, h will cancel out, 2 will go up, and this will be lambda 2 lambda 1 lambda 2 over under the root lambda 1 square plus lambda 2 square. Okay. Now from these given options, option C is the right option. Okay. So option C is the right option here. Now let's move to question number 2. The electrons are accelerated through a potential difference V and protons are accelerated through a potential difference 4V. The de Broglie wavelengths are lambda E and lambda P for electrons and protons respectively, and we need to calculate the ratio of lambda E and lambda P. Okay. So what question says to us, अपने पास electrons हैं and protons, both are accelerated by V and 4V volt. Okay. तो हम simply लिख लेते हैं कि let's say if we are creating a potential difference of V volt, okay, and if we are accelerating a charge Q by these, then simply by using conservation of energy. So what can be written as the electrostatic potential energy can be written as QB plus kinetic energy is 0, and at this plate, if I'll assume potential here is V and potential here is 0, because the potential difference is V, then what we can write is QV plus 0 is equal to, we can write the kinetic energy at plate 2 kinetic energy at plate 2 is, let's say, K plus potential, electrostatic potential is 0. Now by using conservation of energy, we can write the kinetic energy is simply Q into V, where Q is the charge and V is the potential difference by which the charge has been accelerated. Okay, so and also we know that the momentum is related as P is equal to under the root 2 times of kinetic energy of the charge multiplied by mass of the charge. Okay, and also we know that by using de Broglie equation that lambda is equal to h by p. Okay, now simply using these we can write lambda is equal to h over 2 times of kinetic energy into mass, and in place of kinetic energy we can simply write lambda is equal to h by under the root 2 q v into m. Okay, now let's put all the values here. Let's say lambda e is the wavelength of electron, then it can be written as h over under the root 2 times of charge on electron multiplied by the accelerated potential multiplied by mass of the electron. Similarly, lambda p can be written as h over under the root 2 times of charge on proton, which is same, into accelerated potential. Accelerated potential here is 4v. Okay, so 4 times of v into mass of proton. Now we can easily write the ratios. Lambda e over lambda p, that is that can be written as h over under the root 2 times of e v mass of electron into 2 times of e into 4v into mass of proton over h. Okay, h and h cancel out. Simply we can take this 4 out, that will make it 2. Okay, and rest of this will cancel out. Okay, so simply lambda e over lambda p can be written as 2 times of mass of proton over mass of electron. Okay, which is option number D in these given options. Okay, now let's move to the question number 3. K alpha is the wavelength emitted by an atom of atomic number 11. Okay, K alpha wavelength emitted by an atom of atomic number Z is equal to 11 is lambda. Okay, so for atomic number Z is equal to 11, the K alpha wavelength is simply lambda here. Now find the atomic number of an atom that emits K alpha radiation, which is 4 lambda. Okay, so we need to find out value of Z for which the K alpha wavelength is 4 times of lambda. Okay, now let's write down the, so we can make use of Moseley's law here to find out the relation between K alpha and Z. We know K alpha, or for K alpha wavelength we can write using Moseley law, frequency is directly proportional to Z minus A, or we can write, sometime books mention Z minus B. Okay, so for K alpha B is 1, so mu is directly proportional to Z minus 1. Okay, now we know mu and lambda, they are related as mu is equal to C over lambda. So this can be written as a constant A into Z minus 1. Okay. Now, now simply putting up all these values, we can write C over lambda for first case is equal to A into Z. Z is 11, 11 minus 1, which is 10 over, okay. And then for the second case, let's say this is lambda 1, or which is lambda here. For second case, C over 4 lambda is equal to A into Z minus 1. So from using these two equations, we need to find out the value of Z. So let's divide both of them. Simply A will cancel out, lambda and lambda, C will cancel out. This means 4 times of Z minus 1. This simply gives us, okay, 4, 2.5. That is, so this will give us something which is Z minus 1 and 4, 11. So we can easily write 11 and 4, find the atomic number of where K alpha 4 lambda. So we can write A Z minus 1, and this can be written as A is cancel out, B okay. So for K alpha wavelength, let's for K alpha value of B is okay. Yeah, okay, so we missed out something here. That's what I was looking at. So this must be root mu using Moseley law, and this must be this. So we can write this Z square here, okay, squaring both sides. So sorry, so this, let me delete it, okay, and we can write here that C by lambda is equal to A, putting Z is 11 here, so that will give me Z minus 1, which is 10 square 100, and in second case that is C by 4 lambda, and this is A Z minus 1 whole square. Okay, now we need to find out the value of, so simply putting up value of C by lambda here, that is 100 times of A divided by 4 is equal to A Z minus 1 square. Okay, A and A will cancel out, this will become 25, and Z minus 1 whole square will become 25. This will give us Z minus 1 is equal to 5 and Z is equal to 6. Okay, so the right answer is A here. Sorry, the right option is A. Okay, now let's move to question number 4. The magnetic field associated with the light wave is given at the origin. So we are given the magnetic field. We know light is an electromagnetic wave, and this question is giving us the magnetic field associated with the light, which is B naught sine of 3.14 into 10 raised to power 7 CT plus sine of 6.28 into 10 raised to power 7 CT. If this light falls on the silver plate having a work function of 4.7 electron volt, what will be the maximum kinetic energy of the electrons? Okay, so simply if we look into this function, this can be written as the sum of two magnetic fields, okay, which is simply B naught sine of 3.14 into 10 raised to power 7 CT plus B naught sine of 6.28 into 10 raised to power 7 CT. Okay, if we look into this function, then the maximum frequency, so we can simply write down that, okay, there is a silver plate and the light which is incidenting on this plate is actually having these type of magnetic fields, okay, these two. So simply, if this magnetic field, or which is simply carrying the magnetic energy, or the which is representing the energy of the electromagnetic wave, so the electron which will be emitted by the high frequency wave will have the larger kinetic energy. Okay, so we'll stick to this rule, and just simply comparing it with the function that B is equal to B naught sine omega t. Okay, we can write, we can clearly see that the second function has the larger value of frequency, which is simply omega is 6.28 into 10 raised to power 7 times of c, okay, which is c is speed of light. Okay, now frequency can be written as omega is equal to 2 pi f, which is 6.28 into 10 raised to power 7 into 3 into 10 raised to power 8, which is the speed of light. And 2 pi is, if I'll take pi as 3.14, then this will simple cancel out, 2 pi and 6.28. The frequency incidenting is 3 into 10 raised to power 15 hertz. Okay, now value of h is also given, and the work function is given in terms of 4.7 electron volt. So phi is given as 4.7 electron volt. Now if we'll use this simple equation of photoelectric effect, then we can write that the energy of the photon must be equal to the work function plus Ke max. Okay, now from here Ke max can be written as energy of photon minus work function. Okay, now energy of photon can be calculated, because we need to calculate that in electron volt, because phi is given in electron volt. So energy of the photon in electron volt can be written as, we can easily write it just by using simple equation that EP is equal to 12,400 over lambda in angstrom. Okay, now lambda can be calculated as, okay, we can write this frequency and lambda is c by f, and this lambda is in, we can get c as 3 into 10 raised to power 8 over 10 raised to power 7 into 3 into 10 raised to power 8. That will cancel out. So this lambda we will be getting is in 10 raised to power minus 7 meter. Okay, and we know in 1 meter there are 10 raised to power 10 angstrom. Okay, so lambda can be written as 10 raised to power minus 7 into 10 raised to power 10, which is 10 raised to power 3 angstrom. Okay, 10 raised to power 3 angstrom. Now this 10 raised to power 3 angstrom, EP can be written as 12,400 over 10 raised to power 3, which is 1000. So that can be written as 12.4 electron volt, because this energy is in electron volt. Okay, now we need to find out the kinetic energy max. So kinetic energy max can be written as, now using this equation we can write energy of photon, which is 12.4 minus the work function, which is 4.7. Okay, this will give us 0.7 and something like 11, no, sorry. Oh, oh, oh. This will give us something like 8.5. So this will make us 0.7 and 11.4 7.7 electron volt, sorry. So 7.7 electron volt. So which is close to the 7.72 electron volt. Okay, so the right answer is D here. Okay, now move to question number 5. Here in this question it is given that particle A of mass ma is equal to m by 2 moving along the x-axis with velocity v naught, and it collides elastically, make sure we note down this word, elastically, with another particle B at rest having mass mb is equal to m by 3 if both particle moves along the x-axis after the collision. Okay, the charge, sorry, I think the change, it must be change. Okay, the change delta lambda in de Broglie wavelength of particle A in terms of de Broglie wavelength lambda naught before collision is. Okay, so what question tells us that we have a particle which is a particle B whose mass is mb, and mb is given as m by 3, and there is another particle A which is moving, the mass of the A is m by 2, and this is moving with velocity v naught. Okay, so first let's find out lambda naught. Okay, what is lambda naught here? So lambda naught is nothing but that is the value of h over the mass ma, which is m by 2, so 2 mv naught. This is the value of lambda naught. Okay, because we need to tell delta lambda, which is change in length of particle, wavelength of particle A in terms of lambda naught. So we need to calculate lambda naught first. Now let's find out the value of the wavelength of the particle A after collision. Okay, now because this is an elastic collision, so anyway we can make use of conservation of momentum here. So initial momentum, which is m by 2 v naught, must be equal to the final momentum. Okay, and this is elastic collision, so we can write m by 2, let's say the velocity after collision is v1 and this velocity is v2, so m by 2 v1 plus m by 3 v2. Okay, now from here we can easily write down that v naught is equal to or v naught by 2 is equal to v1 by 2 plus v2 by 3. This will give us 6 and so 3 v naught is equal to 3 v1 plus 2 v2. This is equation number 1. Okay, now we can, because this is an elastic collision, we can easily make use of coefficient of restitution here, which is E for elastic collision is 1, and that is velocity of separation, which is v2 minus v1 divided by velocity of approach, which is v naught. So using this we can write v2 minus v1 is equal to v naught. Now we need to find out v1 anyway, because we need to just find out the change in wavelength. So let's write down the value of V2 as V0 plus V1. So putting that in equation number 1, we'll be getting 3V0 is equal to 3V1 plus 2 times of 2V0 plus 2V1. Okay, so this will give us V0 is equal to 5V1, and 5 from here V1 is V0 by 5. Okay, now the final momentum of the particle A can be written as final momentum of particle 1 is m by 2 mass of the particle into V0 by 5. Okay, now we know that the final wavelength, let's say that is lambda 1, it can be written as h by final momentum, which is nothing but 10 times of mv0 into h. Okay, now we need to find out the change. Now change is final wavelength minus initial wavelength, which is 10h by mv0 minus 2h by mv0. Okay, that will give us 8h by mv0. Now this can be written as 4 times of 2h by mv0, and 2h by mv0 is nothing but that is lambda naught. So delta lambda can be written as 4 times of lambda naught. So out of these given option D matches the calculations. So option D is the right option here. Now let's move to the next question. Here again it is given that an electron of mass m with initial velocity v is equal to v0 I cap plus v0 j cap is in an electric field of E0 k cap. Okay, if lambda naught is the initial de Broglie wavelength of the electron, its de Broglie wavelength at time t is given by. Okay, so let's first draw the diagram what exactly this electron is doing here. So we have the electric field which is in k cap direction. Okay, which is nothing but E0 k cap. Now let's say the electron, we know that electron is moving initially, the electron is moving in V0 I cap and V0. So this is V0 I cap and this is V0 j cap. So I would say the electron is somewhere moving in this direction. Okay, good. So now we need to find out lambda naught is the initial de Broglie wavelength of the electron, its de Broglie wavelength at time t. Okay, so let's first find out what will happen to the electron after time t. Okay, so we can easily write down in x direction we have initial velocity which is v0. In y direction the initial velocity is uy is equal to v0. In z direction the initial velocity is 0, whereas ax is 0, ay is 0, and az, because the electron is a negatively charged particle, that's why the force on this electron due to this electric field will be in opposite direction. So the electric field will be continuously working on this electron in this direction. Okay, So, and this force will be simply charge on the electron into E naught. Okay, and this is downward. So, but we can always write down that this is in minus of. So, if we want to calculate the acceleration on the electron, then that will be only in z direction because the force is in z direction. So, E naught by mass of the electron, and that's in negative. So, I would write minus here E naught by m. Okay. Now, let's say after time t, because there is no acceleration in x direction and in y direction, there is no change in velocity in x and y, but the velocity in z direction will change, which was earlier 0. So, now Vx is ux plus ax into t. This will become 0. So, Vx is still V naught. Similarly, here Vy is still V naught. But in this direction, Vz is equal to uz minus E naught by m into t. Okay. Now, the final velocity of the electron can be written as V naught I cap, V naught j cap minus E naught by m into t k cap. Okay. Now, the speed of the electron can be written as, okay, let me write it here. I'll use this, okay, or I'll move it completely. I'll move this whole stuff here. Okay. Okay. Let me just move it. Okay, leave it. So, I would write here that V is equal to under the root V naught square plus V naught square plus E square E naught square by m square into t square. Okay. Now, the final wavelength can be written as lambda final is equal to h over m into under the root 2 V naught square plus E square E naught square by m square t square, which can be written as h over m, and this will become root 2 V naught, and this will become 1 plus E square E naught square divided by m square 2 times of m square V naught square t square. Okay. Now, initial momentum can be written as m times into the resultant of these root 2 V naught, which is simply root 2 V naught. Okay. Now, we can replace this with this is simply the initial wavelength. So, final wavelength can be written as the initial wavelength divided by under the root of 1 plus E square E naught square by 2m square V naught square into t square. Okay. This is out of the given option is option number C. Okay. Now, let's move to the next question. Question number 7 here. Now, question number 7, a beam of electron of energy E scatters from a target having atomic spacing of 1 angstrom. Okay. So, we are given the atomic target whose layer spacing is this is given 1 angstrom. Okay, the first maximum intensity occurs at theta is equal to 60 degree. Okay, now if you have studied the the Bragg's law of X-ray diffraction, this question belongs to that. So let's say if these are the particle which are striking the atom, and let's say if this is the angle 60 degree. Okay, now these particle will go there. Similarly, let's say there is another ray of particles which is coming here, so that will strike to this point. Okay, now they will go back, and both of these two waves, they will interfere with each other. Okay, and they'll create the diffraction pattern. Okay, now let's just simply solve it. Now we need to just find out the path difference and write down the condition of maxima here. And we know condition of maxima is delta x is equal to n lambda, and delta x is the path difference between the two waves. Okay, so we can write here, draw a simple perpendicular, this, and simple perpendicular here. This plus this is the path difference between the two waves. Now let's say if this is d, which is simply the interatomic separation. Okay, d, and if this angle is theta, then this is 90 minus theta, then theta, this angle is theta. Okay, so this can be written as d sine theta. Okay, this can also be written as d sine theta. Okay, okay, theta and theta. Okay, and okay. Now delta x is equal to 2d sine theta. Okay, EV. Okay, then E we need to tell in. Okay, and this is creating the first maxima. Now condition of first maxima is n is equal to 1. So lambda can be written as delta x by n, and delta x is 2d sine theta, and n is 1, so simply 2d sine theta. Okay, so now 2d sine theta, this will give us 2, d is 1 angstrom into sine theta is root 3 by 2, that will give us root 3 angstrom. Okay, now this will give us root 3 angstrom. Now E can be written as 12,400 divided by lambda in angstrom. Okay, 12,400 and this we need to tell in. Okay, okay, this is in EV. So lambda is 2d sine theta root 3, that's okay, and this is nothing but 12,400 divided by lambda in angstrom, which is 1.7. This will give us approximately 119. So this will give us 2d sine theta, which is 1.7. If I'll take root 3, then that will become 1000. So 17 17 approximately 750. Approximately 750, am I right? If I'll remove this one, then this will become 12,000 divided by 17. Sorry, 7300. Okay, approximately 7300 electron volt. Okay. Then E in electron volt is this. Okay. Now move to question number 8. An electron moving with speed v and a photon moving with speed c have de Broglie wavelengths. The ratio of kinetic energy of electron to that of photon is. I think this question is incomplete. An electron moving with speed v and a photon moving with speed c have de Broglie wavelength. There is something missing here. Let me check. Let me check what is missing here. An electron moving with speed v and a photon, okay, having same de Broglie wavelength. See, having, this must be having same de Broglie wavelength. Okay, it looks like have same ratio of kinetic energy of electron to the photon. Okay, yes, they have same de Broglie wavelengths. Okay, now let me just write down. It is given that de Broglie wavelength of electron, which is lambda e, that is lambda e is equal to nothing but that is h by mv, or we can say h over under the root 2 times of kinetic energy of the electron into mass of the electron. Okay, and the photon a photon having the speed c. So lambda is the photon, the wavelength of the photon, and that is simply h by the momentum. So momentum of the photon can be written as momentum of the photon momentum can be written as h by lambda of photon, but that they are both equal. So simply we can write that this means and lambda p is equal to h and momentum of the photon, but that is equal to h by mv. So simply we can write photon momentum is equal to momentum of the electron. Okay, okay, so photon momentum is momentum of the electron. Kinetic energy of the electron, kinetic energy of electron can be written as half mv square, and ratio, and to the photon, kinetic energy of the photon can be written as which is simply mc square. Okay, and if I write this, kinetic energy of the photon, kinetic energy of the photon can be written as kinetic energy of the photon can be written as the momentum of the photon into, we can write simply momentum of the photon, the momentum of the photon into speed of the photon. Okay, that can be written as mv, because photon momentum is still mv into c. Okay, now if we'll take ratio of both, v will cancel out. This will become kinetic energy of electron to kinetic energy of photon is equal to v by 2c. Let me check if this is the right one. I think the option is given here, but if I have done it right, then yeah, this was the question actually. So this word was same. Okay, so v by 2c. So option number C is correct. Now let's move to the next question. There are two identical photocathodes receive the light of frequencies f1 and f2 respectively. If the velocities of the photoelectron coming out are v1 and v2 respectively, then okay, so the question, it's given in question that there are two photocathodes. Okay, let's say this is the 1 and this is the 2, and receive the light of frequency. Both are receiving the light frequency f1 and f2. Okay, then the velocity of the electrons, the electron which are coming out are having velocities v1 and v2. Then we just need to find out the relation between these two. Okay, so two identical. Okay, this means their phi's are equal. Okay, so we can write down by using photoelectric effect that h times of f1 must be equal to phi plus k times of 1, and h type of f2 is phi plus k2. Okay, now simply we need to find out, let's simply subtract them. So this will give us k1 minus k2 is equal to h times of f1 minus f2. Okay, k1 can be written as half m v1 square, k2 can be written as half m v2 square is h times of f1 minus f2, and this will give us v1 square minus v2 square is 2h by m into f1 minus f2. Okay, this is option number 1. Okay, now question number 10. The kinetic energy of emitted electron is E when the light incident on the metal has wavelength lambda. To double the kinetic energy, the incident light must have wavelength. Okay, now the kinetic energy of electron is E. Okay, now let's say this is the photosurface, the light is incidenting on this, and let's say this has wavelength lambda, and the electron which is emitting here has energy, kinetic energy at E. So we can write down hc by lambda is equal to phi plus E. Okay, now we need to double the kinetic energy and we need to find out the new wavelength. Okay, so simply now let's say hc, and let's say the new wavelength is this lambda dash, then this is phi plus E dash. Okay, now from here we want twice the kinetic energy. So if you want twice, then let's make it 2 times, 2 times, and 2 times. Okay, then from here we can write 2 phi is equal to 2 hc by lambda dash minus 2 E dash. Now from here we can write 2, 2, and 2. Okay, from here 2 phi can be written as 2 hc by lambda minus 2E, and both must be equal. These two must be equal. So we can write 2 hc by lambda dash minus 2 E dash, and E dash, in place of E dash we can write, yeah, the new energy must be twice. Okay, let me, I think I have missed out something here. I think I have missed out something here. So we need to find out that lambda dash, let me recorrect it. We need to find out, or I'll rewrite the complete thing. This is hc by lambda must be equal to phi plus E, and we want hc by lambda dash must be equal to phi plus 2E. Okay, now simply substituting the value of phi will give us hc by lambda minus E is equal to phi. Okay, now dump this equation here, so we can get hc by lambda dash is equal to hc by lambda minus E plus 2E. Okay, so this will give us hc by lambda plus E. Okay, we need to find out lambda dash now. Lambda dash is nothing but lambda dash will be, just cross multiplying and divide again, hc divided by hc over lambda plus E. Okay, and this will give us, lambda will take hc by hc lambda hc plus E lambda. So this is the option number B here. Okay, now let's move to question number 11. The ratio of de Broglie wavelength of an alpha particle and a photon accelerated from rest by the same potential is 1 by root m. The value of m is, I think this is going to be an easy one, because again the concept is still same. Let's say if this plate potential is V and this is 0, and if we have one alpha particle and other is a photon, a photon, I think it must be proton, because photon we cannot accelerate photon, it must be proton. Okay, proton, yes, we cannot accelerate that, it must be proton. Okay, now we know here the kinetic energy of the alpha particle can be written as the Q of alpha into V, and kinetic energy of proton can be written as charge on proton into V. Okay, now we know that lambda of photon, lambda of alpha particle is equal to h over under the root 2 of kinetic energy of alpha particle into mass of alpha particle. Similarly, lambda of p is h over under the root 2 over kinetic energy of proton, mass of proton. Okay, Now they are accelerated to rest by same potential, then their ratios are k 1 by root m. So we'll write this is simply 1 by root m. So we can write 1 by root m is equal to h over h, and this can be written as 2k times of proton and mass of proton, 2k of alpha and mass of alpha. Now simply write down, we'll get 2 kinetic energy of proton. Let's say E is the charge on proton and mass of the proton is m, divide by 2 alpha particle. We know that is having twice the charge on the proton, which is 2e, and this is 4 times of mass of proton. Okay, 2 and 2 cancel out, m and m, e and e. So 1 by root m is equal to 1 by root 8. So m is equal to 8. So let's move to the last question. A point source of 100 watt emits light with 5% efficiency. So we have a point source which is of 100 watt and it's emitting light and its efficiency is 5%. Okay, so this means a receiver is actually or I would say though it's consuming 100 watt of power, but actually it's emitting 5% only. So really it's actually emitting, the power output of this bulb is 5 watt only because of efficiency of 5%. So we can redraw it that there is a source of 5 watt. Okay, at a distance of 5 centimeter from the source. So distance is 5 centimeter from the source. The intensity produced is I. We know I is equal to power upon area of the sphere. Okay, so this can be written as power upon 4 pi. If this distance is d, then 4 pi d square. Power is 5 watt. 4 pi, okay, the answer is in pi, so we'll keep it in pi, into d square is 5 into 5, but that's in centimeter, so we'll raise 10 raised to power minus 2, that will become 10 raised to power 4 here. Okay, so 5 and 5 cancel out and this will become 20. So 100 into 100 over 20 pi, that will make us 5 meters. Sorry, it was 5 meter. Okay, it was 5 meter. Sorry, I missed it. It was 5 meter. So if this was 5 meter, so let me recalculate it. This still remains same. Everything, power is 5 watt. And this will become 4 pi. D square will become 25 now. This will become 20 pi watt per meter square. This means B is the right option now. Yes, thanks. Thank you guys.